What is a zero? Where are we? Newton's laws, Kirchhoff's laws, considerations, domain expertise, etc. Y dot to dots equal to f of something. Linearization, impulse response, and transfer function. So those two are the objects that we use to compute free evolution and force response that in our intuition is the forecast that we do. This one here, very often, the impulse response, the transfer function very often is numerator of S, denominator of S. What is the denominator of S? Denominator of S, whenever we factorize it as product of poles, those ones, and also actually the multiplicities here, let's call it Ni, they tell us the shape of the modes of H. True? For example, if I see an impulse response that looks like this one, this is time, and this is my impulse response that I measured, where are the poles? Real part, imaginary part. Sigma, omega. Go, discuss. This, of course, it's something that looks like this exponential. Like, you got the point. How does it continues like this? How does the H of S look like in terms of poles? Go, discuss. So people, what do you say? Are we going to have something here? Yes, no, do not know? No, true. Something here. Does anybody want to say where the crosses are? Yes. Yeah. How many? Where? Where do I put them? I give the solution. 1 and 2. Why? This object here is decomposable as this mode plus this mode. Sorry, this one is done in a bad way. True? Do you see? Green plus blue. True? How much are we together, people? 1, 2, 3. Okay? Vivo stable? Yes, no, do not know. No, which input, bounded input leads me to an unbounded output. Start. True? Perfect. We are together. Now, this tells us how to divide things, or better, what are the modes? Does this plot tell us how big the modes are? No. We do not know. Whenever we do partial fraction decomposition, we do not know the residuals. True? We might have 7 step plus 0.02 e minus p. True? Or we might have 107 and 1002. True? Those ones, those numbers are called the residuals associated to the modes. Okay. Where do they come from? They come from the partial fraction decomposition. That means what is this? What is this? And what is there is essentially influenced by what we call zeros of a function. Those ones are the poles because in Laplace they look like a kind of the stuff here. If you look at the modulus, are we together? Are you following me? People want to say? Perfect. This one on the numerator is a polynomial. The objects that are there, or better, the factors of that polynomial are gonna be called zeros. And now we investigate what those zeros are from a physical perspective. Okay? So, question.
If you got an exponential and a transfer function that increases, that would have like the transfer function in the right part of the sigma positive.
If I have something that looks like this pole,
Yeah.
What is the question?
We have an exponential that is.
We have an exponential that looks like in time, something like this, or something like this, depends on the residual. True. Okay. Together, there is we know that it's an exponential. It might be minus 0.2 e plus t. True. And then it does something like this. Okay. Force, mass, spring. Do you see it? Do you see it? Do you see that you might imagine in your head that for an opportune combination of the coefficients and an opportune combination of the masses and an opportune frequency of how much the force is pushing, this one stays there. You see? And the analytical expression, to be honest, I never found it, but you have the feeling that if you combine things in an opportune way, there must be a certain specific frequency for which this one stays there. Are we together? 1, 2, 3. Let's pretend now that we have U is the force and Y is this position here. How is the system looking like? There's injection of something, U, Y, and it's something, in a certain sense, it's if I throw that specific cosine, that specific omega t, Y stays 0. True? In a certain sense, let's now connect to this one is a linear system. This is LTI. Okay, let's assume it's LTI. If it is LTI, we have sinusoidal fidelity. True? Do we remember sinusoidal fidelity? How much do we remember sinusoidal fidelity, people? Very much? Not at all? Kind of. Sinusoidal fidelity. I inject a sine. After the transient, I get a sine that is amplified and shifted. True? And the amplification and the shifting depends on this frequency here. Are we together? Do we remember this, people? Perfect. Sinusoidal fidelity. Does it apply only to LTIs in general, or you do not know? Only LTI in general, you do not know. Discuss? People, what would you say? What would you say? Only LTIs, because sinusoidal fidelity from a mathematical perspective follows from the fact that the eigenfunctions sorry, exponentials are eigenfunctions of the convolution operator. Or better, sorry. Yeah, of the convolution operator. Do you remember this? I can also revise it. If I have u after it convoluted h, this is going to be the integral of h e. Let's call it this one is e minus t, or better, j omega t. It's going to be even better. This is going to be j omega tau minus t. True? And then this one, I decompose it into e j omega tau, e j omega t minus the tau. This one pops out, true? Because the integral is tau, and then we are happy. We have an eigenfunction. True? The stuff that remains is going to be the stuff that's going to give me in the limit, the amplification and the shifting. How much are we together, people? Do you remember this part? If you don't remember this part, you've got to go back and recheck it. Okay, this is important. Together, either that we are there or that you've got to rewatch it. 1, 2, 3. Excellent. What are we using then? This fact here we are using convolution. What does it mean to use convolution? Implicitly, it means that we are using superposition effects. When do superposition effects hold? Only for SDI systems. Is the chain clear, people? 1, 2, 3. Excellent. Okay, let's go back to our zeros. We have a specific oscillation that gets killed. And it's a specific oscillation that depends on the various parameters. True? Together? Moreover, this one is an LTI system. And for this one, we have sinusoidal fidelity. And in a certain sense, it still preserves sinusoidal fidelity. What we are saying in this specific situation is that for that specific system, the gain for that specific omega is 0. The amplification factor is 0. See, what does it mean to have a 0? It means that there are some sinusoids that gets, how do you say? They don't pass. Do you remember from a Laplace perspective? So no. You remember from a Laplace perspective, sigma, omega, and then we have modulus of h, and then we have the blanket, and we are saying that eventually this sinusoidal fidelity thingy, we see it as the cut that we have on the omega axis. So we remember. That means that if I inject a cosine omega t as u, with this omega being this stuff here, and this one is 10, it means that after the transient, my y steady state is going to be essentially 10 cosine that omega t, sorry, plus a shift. True? Together? In this situation, we have an omega bar for which we have 0. How does this blanket look like? How does that blanket of that system have to look like to have this property that one of the sinusoids gets 0? Madonna Santa bene. No, it's no, I think I've got some problem. I think I have some neurological disorder at this point. Do you remember? Do you remember the plot where there was like the mime animation with three poles and there were like the two zeros? You remember that one? Yeah, the two zeros were kind of bumps in the blanket. So yeah, there are two. We need to have two bumps so that the blanket touches zero there. So to have zero amplification. Are we together? Do you see, people? Now, formal definition of a zero. The zero of a function is a value zi such that if I plug it inside the function, I get zero. Okay? Does a zero need to be on the omega axis? No. Look at this. S minus plus 3 divided S plus 2, S plus 4. Where is the zero? Minus 3. How do we indicate it? Zero. Okay? So watch out. Something that might, my discussion before might have kind of made you think. This specific case here is a special zero. In which sense? It's a zero that is on the imaginary axis. But in general, it might not be in the imaginary axis. And now we are going to see the effect of moving the zeros around. Okay? Together? Perfect. This is the definition in general. And of course, whenever we consider a transfer function and we consider an h of s, what do we have? The stuff that we were saying before with the transient and the convolution operator, from a formal perspective, if I take u of t, any generic complex exponential, the y of t is going to be the complex exponential times the transfer function evaluated there. Okay? Are we together? This is the eigenfunction, the composition of h whenever we do the convolution. It's slightly wrong because this is the forced response, actually. This is the forced response. I write to myself so that I do not bother you. Damiano. 5. Then I will remember. Now, are we together on this, people? This object here, has it to be a sinusoid? No. That object here is depending sigma omega where I take S bar. If I take this one, this object here is going to look like, how does it going to look like? Let's see. You tell me. T, real part, imaginary part. If I take these as minus 10, 5, how does this signal look like? It's a spiral, true? It's a spiral that rotates in a certain way and compresses, true? Together. What is going to be the forced response? It's going to be the same spiral, amplified, and shifted in terms of phase. Are we together? Hmm? The amplification factor, how is it? Let's make the same example as before. And now you're going to see, and you will say, it had to be like that. Let's take h made like s plus 3 divided by s plus 2, s plus 4. Hmm? Now, we take as exponential here e minus 3t. How is the Laplace transform of this one? One over s plus 3. Whenever I compute the force response, what do I have to do? The product of the two, true? What happens to y? How is y going to look like? True? We have a cancellation. Hmm? Now, this is not the whole story. This is not the whole story. Making your life more difficult instead, actually, in this way. Let me reorganize just a moment what I want to say, because I'm kind of leading, I'm skipping ahead. I wanted to show you a different thing. The fact is that if this one is 0, this one is going to be 0. And I've got some error somewhere, because whenever I take this object here and I take this transfer function here that was the one before, this one has to come out 0. And it's not coming out anymore. Ah, no, because I'm stupid. Because I'm stupid. Because I'm stupid. Because it's this is y. And instead, I want to have h of s. And h of s, this is not the first response. This is the steady state. This is the mistake. Okay. Sorry. It's the steady state. This is the mistake that I'm doing. The mistake that I was doing is this one. I restate. I restate in a way that it's correct. The mistake of not writing this one in the correct way and me messing up between force response and steady state made me do computations that were wrong. Now we revamp everything. Whenever we were discussing about the convolution and the exponentials that are eigenfunctions, this stuff here refers to the steady state. True? To the stuff that in a certain sense stays there. Let's redo it. Y is h times u. True? If I look at stuff in terms of process, sigma, omega, let's make h in black and u in blue. This one applies to, this is the sinusoidal fidelity, and this one applies to the mode that stays. The mode that stays are those ones. Are we together? Are you following me, people? 1, 2, 3. Perfect. Whenever I do this formula here, I'm computing a specific object. I'm computing the steady state. Before, I was having this situation here with the example as before. And maybe it's, should kind of do the slide in that way. I was having sigma omega. Then I was having u that was this pole. True? And then I was having H that was this, I don't remember anymore. I think it was this pole, and this zero. True? Let's rewrite it. We were having U that was S plus 3, S plus 2, S plus 4. True? Sorry, this was H. Madonna Santa. This was 1 over S plus 3, and H was S plus 3, S plus 2, S plus 4. Are we together, people? How much are you following me? Oh, I see some twos. Why some twos? Okay, but what are you not following? So this one is the example as before, the numerical example. Are we together that this is the numerical example? Okay. Now, I want to apply this formula here. This formula here refers to the steady state, the stuff that is going to stay in steady state. Okay? In steady state, what are we going to see? Nothing. It's going to go to zero. True? Are we together that y is going to be 1 over s plus 2, s plus 4? Are we together? And are we going to be together that y steady state of t is going to be, due to the sinusoidal fidelity, this exponential h evaluating that exponential? That h evaluated in that exponential is going to be 0, because this is minus 3. Together? Together? So essentially, we are kind of a zero of a cluster function indicates a type of exponential that doesn't go through. I think it's the worst term.
So when we have a zero, what we see is that the steady state response is actually zero, because from that equation we see that transfer function.
Indeed.
Okay.
Indeed.
Zero necessarily.
Let's do it here. Let's do it here. Let's do some examples so that we are together. This is my transfer function. Okay. This is a transfer function that has got a triple pole here and double zero here. Or double, it's a single zero, but it's a complex conjugated zero. Are we together? This is my h. If I inject u of t, that is this object here, y steady state, is it going to be equal to 0, different, equal to 0, different from 0, or you do not know? Discuss about it. Think what is that? Think at the blanket. Think at the blanket. What would you say, people? 1, 2, 3. Different from 0, because eventually, if you think at the blanket, it's a blanket that touches here, but for the x's that we are considering, we have an amplification factor that is different from 0. True? we're seeing it? Perfect. If now I take the u and I put the crosses closer to the zero, that means I make a sinusoid that is slower in frequency too. See me? The steady state in amplitude will stay the same amplitude as before. Will go up in amplitude, will go down in amplitude, or you do not know. Will go in amplitude, the amplitude of the sinusoid in output. I've got the same sinusoid in input with a different frequency. Before I was having a certain sinusoid in output. Let's say this one was the first one, the first case. Now, do we go smaller? The frequency. Is it going to change the frequency? Of course it's going to change because this one changed. True? Together? Perfect. But the amplitude, is it going to be staying as before? Is it going to be bigger than before, smaller than before, or you do not know? Of the output. Of the output. First case, second case. True? The second case, we are getting towards the zero. True? The amplitude is going to become smaller and smaller. True? At the limit, whenever I choose the same frequency, if I inject u of t that is on top of the zeros, what do I get? Zero. Together? Let's see another case. Let's see another case. Let's see if you see this one because it's an important. And then we go back to the formulas before. If I have a system that looks like this one, look at it. Look at it. Okay. Hmm? And I inject a sinusoid that is here, omega 2t, omega 2, sorry. Will I get zero output? Yes, no, I do not know. Discuss. People, what would you say? No, because we have a cross and a cross. This one, there is a complex exponential. For that one, there is already zero. For this one, the complex exponential, that one is not a zero. The residual will be different from zero. The output is going to be what? Some imaginary, some complex number, some complex symbol. Okay, but indeed, the system is complex. It's not real. True. We don't have. We've got a j here that appears. The parameters are imaginary. Okay. something that from a physical perspective doesn't have too much sense. Are we together, people? Are we following? Do you feel like? Now, if I inject a sinusoid here, are we going to get out a signal that is different from zero? Yes. If we are going to get this sinusoid as alternative input, what do you expect to see as an output? Do you expect to have with output 2 as amplitude? Is it going to be bigger, equal, smaller than the amplitude of the first one? You see, I do not know if I said it in the correct way. I inject u cosine of this omega or cosine of this omega, and then I get y1 or y2. Okay, together, y1 will have a certain amplitude. Y2, will it have a bigger amplitude, the same amplitude, smaller amplitude than y1? People, what would you say? Smaller in amplitude, why? If you think at the blanket that is defined by this situation, we have a pole and two dips, true? And the dips, in a certain sense, radiate the level, true? Do you see, people? Here, I'm gonna meet the blanket where the blanket is higher than here. Let's do a numerical example. Let's do a numerical example so you will see. Or I think that I've got also some plots. Those are plots. Those are interesting plots. I think that we use those ones. This is the transfer function that is parameterized by alpha. And alpha can be basically defining this or this or this, depending on the value. I will have a certain step response. This is the step response. This is h of g. You see it? Then. Now, for alpha equals to 0.1, what is happening? We have a cancellation, true? And indeed, for alpha 0.1, we have only this mode here. But for alpha different than 0.1, we have pole, 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 and either the 0 or the 0. Together? Do you see that? There is an exponential here. True? And it's an exponential that goes down with the same time constant, and the oscillation is also with the same frequency, because it's defined by this pole. Do you see that that pole defines an E sigma t cosine omega t with a specific sigma, specific omega? But do you see how the amplitude of that mode depends on the 0 position? You see that somehow 0.025, you are closer to the pole. 0.5, you are farther from the pole. And you see that in a certain sense, the amplitude of that mode depends. A 0, the effect of a 0 is kind of dampening out the modes. Let's make another example that we see. S plus 0.9, S plus 1, Let's put 1.9, s plus 2. Find, let's make it, this is y. Find y of t. Go, you do it. Numerically, go. How do you do partial fraction decomposition? Are we together, people? Did you? I got it. I would have gotten it. I'm lost. I would like everybody to answer, people. I got it. I would have gotten it. With 2, I'm lost. Excellent. If I put this stuff here, how will those two numbers change? This one is going to become this one, and this one is going to become this one. True? And if I put this one, do you see how making these 0 get closer to this pole? This mode here goes down, or better, this mode here gets a residual that goes down, and this mode here gets a residual that goes up. You see? Okay. The position of the modes modulates the mode. Question. By placing a pole, a 0, close to a pole, the residual associated to that pole gets diminished. If I have, now we discuss about control systems, okay? A control technique that you will see later on in your life. Sigma omega, to make it very short, you've got some poles of the open loop system, and by doing a closed loop system, you place the zeros, you place some zeros where you want, okay? So you can design your control system so that the control system adds in closed loop some zeros, and you might choose the zeros here, here, or wherever you want, okay? If you put the zeros here, what are you going to make? You're going to make the system faster and without overfits. True? You see? Because in a certain sense, the total response will have the modes associated to those oscillations with, they will be e minus 3t cosine 10t. And here you will have, I don't know, 10 to the power of minus 20. Okay? From a practical perspective, that mode disappears. You see? Because placing a 0 close to a pole makes the residual small. Okay? This technique will be zeros allocation. Let's see if you get it. I have an open loop system that is unstable. Okay? This is my open loop system. Okay? And I do a feedback control that allocates the zeros, and the strategy is to do this cancellation. Very good idea. Very bad idea. Don't know of idea. Discuss. To repeat the question, I have a system that if I don't control it, would be unstable because I've got that blue cross on the right hand plane. True? I do a controller that the operation of the controller is I take a 0 and I put it on top of that pole here. Very good controller, very bad controller, you do not know. What would you say, people? What would you say? What would you say? I would like to see your intuitions. I see several threes, some twos, some ones. It's one of the worst ideas that you might have in life because this is a model, true? The blue crosses are models. Are models perfect approximations of reality? No. It might be that you think that the pole is there. Actually, the pole might be, after 1 hour of operation, changing a little bit because the thermal properties change, for example. And then you have a pole that is slightly off with respect to where your cancellation is, true? And you end up with a mode that is like this one, 10 to the power of -7, E plus 3t. This stuff here, how does it behave? It starts very small. Is it going to explode at a certain point? Yeah, true. Are you going to get it immediately that it's going to explode? No, it's going to explode in 1 hour. Is it a good idea? No, true. Are we together? Cancellations, 0 poles cancellations on the left hand plane are very good because eventually if you have some deviation, but you've got something that is this stuff here, I don't care. It's something that goes to 0. True? So the cancellations of the undesired stable poles, you do it. Cancellations of unstable poles, very good. How much are we together, people? 1, 2, 3. Perfect. And other things that we'll do later. Other questions, people? Then we take a pause and we restart